Static versus dynamic load analysis. Welcome to Blueprint to Reality. Today, we're diving into an essential engineering concept, static versus dynamic load analysis. Whether designing a bridge, a high-rise building, or even a simple beam, engineers must understand how different types of loads affect structures. But what exactly differentiates static loads from dynamic loads? Let's break it down. Understanding static loads. A static load refers to a force that is applied gradually and remains constant over time. These loads do not change in magnitude or direction once applied, making them easier to analyze and design for. Examples of static loads include the weight of a building structure, furniture in a room, or the pressure exerted by soil on a retaining wall. Since static loads do not fluctuate, engineers can calculate their effects with straightforward mathematical models, ensuring structures remain stable under predictable conditions. Static loads are typically classified into dead loads and live loads. Dead loads consist of permanent forces, such as the weight of beams, columns, walls, and floors. Live loads, on the other hand, include forces that can vary over time, such as furniture, people, and temporary equipment. Despite minor variations, live loads are considered static when their changes occur slowly and do not introduce significant motion or vibration into the structure. Understanding dynamic loads. A dynamic load, in contrast, is a force that varies in magnitude, direction, or location over time. These loads introduce motion, acceleration, and vibration into a structure, making their effects more complex to analyze. Examples of dynamic loads include wind, earthquakes, vehicle traffic, machinery vibrations, and waves hitting coastal structures. Because dynamic loads create fluctuating stresses, engineers must carefully assess how structures respond to these forces to prevent failure. Dynamic loads can be categorized into periodic, random, and transient loads. Periodic loads include forces that repeat at regular intervals, such as the vibrations caused by rotating machinery or pedestrian movement on a bridge. Random loads, like earthquakes and wind gusts, are unpredictable and require sophisticated statistical and computational methods for analysis. Transient loads, such as sudden impacts from vehicles or explosions, occur over short durations but can cause severe structural damage if not properly accounted for. Comparing static and dynamic load analysis. The primary difference between static and dynamic analysis lies in how motion and acceleration influence the structure. Static analysis assumes that loads are applied slowly, allowing the structure to reach equilibrium without significant internal motion. This makes static analysis simpler and widely used in most building designs. Engineers use principles like static equilibrium and stress-strain relationships to determine how materials and components will react under constant forces. Dynamic analysis, however, requires engineers to account for inertia, damping, and resonance effects. Since dynamic forces introduce movement, they can cause structures to vibrate or oscillate, potentially leading to failure if not properly controlled. For example, during an earthquake, a high-rise building may sway back and forth, and if its natural frequency matches the frequency of seismic waves, it could experience resonance, amplifying the motion and causing catastrophic failure. To prevent this, engineers use advanced computer simulations, time history analysis, and modal analysis to predict how a structure will behave under dynamic loading conditions. Real-world examples and engineering applications. One of the most well-known examples of static load analysis is in the construction of bridges and high-rise buildings. Engineers calculate the dead and live loads to ensure beams, columns, and foundations can safely support the weight of the structure and its occupants without excessive deformation. For dynamic load analysis, we can look at structures like suspension bridges, skyscrapers, and offshore platforms. For instance, the Millennium Bridge in London experienced excessive vibrations when large crowds walked in sync, a phenomenon known as synchronous lateral excitation. Engineers had to modify the bridge by installing dampers to absorb dynamic forces and prevent excessive movement. Another example is earthquake-resistant buildings, where engineers use base isolators, tuned mass dampers, and flexible materials to absorb seismic energy and reduce vibrations. Without dynamic load analysis, these structures would be at high risk of collapse during strong earthquakes. Why dynamic load analysis is crucial. While static load analysis is sufficient for most conventional structures, dynamic load analysis is critical for infrastructure exposed to unpredictable forces. Wind-resistant skyscrapers, high-speed rail tracks, and even sports stadiums must be designed to handle vibrations, oscillations, and sudden impacts without compromising safety. Dynamic analysis also plays a key role in vehicle and aircraft design. Engineers must consider how cars respond to road vibrations and sudden braking forces, while aircraft designers analyze how wings and fuselages react to turbulence and aerodynamic loads. Without these analyses, vehicles and aircraft could experience structural fatigue and eventual failure. That's it for today's breakdown of static versus dynamic load analysis. If you found this topic interesting, be sure to like, subscribe, and hit the notification bell for more civil and structural engineering insights. Stay tuned for more exciting engineering concepts on Blueprint to Reality. Thanks for watching, and see you next time.